Maximum entropy models, an application of the maximum entropy principle. So entropy of a variable capital X is the expected value of the surprisal, as we see given here, and written out. It looks like this in bits, and we're going to be using nats, so this is what it looks like in nats. And notice we're going to index the p's rather than use the p's as a function. But entropy of a capital X is not a function of capital X. To avoid confusion, we're going to look at Shannon entropy as a function of variables, which are the actual probabilities. And we're going to have constraints on those probabilities, and possibly many other constraints, either as inequalities or even topological at times. So entropy is a function that maps probability distributions to the real line. Functions of the form h of p1 to pr, where these are now variables, and their sum is 1 and they're non-negative. And our goal is to maximize entropy subject to constraints. So we have this problem, and here we're subject to at least the constraint, the sum of the p sub i's is 1. We're going to be doing this in nats. This is our objective function is the entropy, and we're going to abbreviate ST for such that, and these are our constraints. And notice I could rewrite this constraint as a function itself, C1 of P1 to PR equals 0, where C1 of P1 to PR is the sum of PI's minus 1. And very often we have several constraints. So optimization with constraints means we use Lagrangian. And we're going to be using sometimes vector notation, where if I write a bold lowercase, it simply means the vector of variables. So bold P is the vector, little p sub 1 to little p sub r. Lambda is the vector of lambdas. And so our Lagrangian is the negative sum, that's the entropy there, and then plus lambda 1 times our first constraint all the way up to lambda k times our last constraint. And h is concave, so in order to find the optimal distribution, p1 to pr, or vector p, we simply need to find where the gradient of the Lagrangian is 0. So the maximum entropy principle is going to look like this. We'll have data as our class labels and functions mapping those labels to a vector space. And they're going to be constrained to have an expected value b sub k. We want to maximize entropy subject to expectation constraints, which are the ones we just mentioned. We're going to number the first constraint that the sum of the probabilities is 1 is going to be k equals 1, and so 1 is b1, and then the others we're going to do 2 to some capital K. We have a theorem that is that the maximum entropy distribution subject to these constraints looks like this. And understanding this theorem is a goal of the video. In general, the maximum entropy principle means maximizing entropy subject to constraints to obtain the system's maximum entropy probability distribution. And a key step here is we're going to use constraints to eliminate the Lagrange multipliers lambda 1 to lambda k. Several examples of this to follow. So in our first example, we're going to maximize entropy subject to only one constraint, that the sum of the probabilities is 1. And this is what it looks like as a constraint function. Here's our Lagrangian with our Lagrange multiplier lambda times our constraint function. And the gradient of the Lagrangian is 0 if and only if the partial of Lagrangian with respect to p sub I is equal to 0 for all I. But when we take the derivative with respect to p sub I of Lagrangian, we get negative log p sub I minus 1 plus lambda. And that's equal to 0 if the natural log of p sub I is equal to negative 1 plus lambda. And this is now our optimal or our maximum distribution p sub I. We solve by taking the exponential on both sides. And now we want to use the constraint to eliminate lambda. The p sub I is either lambda minus 1. It doesn't have any i's in there, so it's just r copies of that. And therefore we can divide and get 1 over r. So our maximum entropy distribution, subject only to the constraint of probability summing to 1, has an argmax of the uniform distribution. All the probabilities the same, 1 over r. Now notice that the key step in this first example was that the derivative of the Lagrangian with respect to p sub I was 0. That implied that the natural log of p sub I star was negative 1 plus lambda. In fact, this step happens every single time. So here's our Lagrangian in general. When we take a derivative, then we're only going to get, in this case, with respect to p sub j, we're only going to get the jth term of the sum, and we're going to use the product rule. So we're going to have the derivative of the p is 1, so we get the negative log p, and then the derivative of the logarithm is going to be 1 over p sub j, but those p sub j's cancel, and we end up with just a minus 1. Now, when we set that equal to 0, then we get the natural log of p sub j is negative 1 plus lambda 1 times the partial of c1 with respect to p sub j up to lambda sub k, the partial of c sub k with respect to p sub j. In other words, the derivative of the Lagrangian with respect to p sub j equals 0 means that the natural log of p sub j is negative 1 plus this linear combination of first partial derivatives. So let's look at our second example. Suppose a process has 3 outcomes, red, green, and blue. P sub r is probability of red, P sub g probability of green, P sub b probability of blue. And suppose that we're given the constraint, in other words, we're told that the probability of green is twice the probability of blue. Then we want to maximize our entropy subject to the sum of the probabilities is 1 and P sub g is equal to 2 P sub b. As constraints, we would have these equal to 0. So we're maximizing our entropy subject to the c sub k functions being 0. And there are 2 of these, and they are the C1, the sum of the probabilities minus 1 has to be 0, and C2, P sub g minus 2 P sub b has to be 0. Here's our Lagrangian, and by our comment earlier, the natural log of P sub j has to be negative 1 plus lambda 1 partial C1 with respect to P sub j partial C2 with respect to P sub j times the lambda 2 summed on the end. Here are our partial derivatives. These are all linear expressions, so I'm not going to go through this in detail, but notice that the derivative of C1 with respect to PR, PG, or PB are all going to be equal to 1. And you can see 0, 1, and negative 2 for the others. So that equation for each of R and G and B is just these logarithms equal to negative 1 plus linear combinations of partial derivatives. Now we can use the values of our partial derivatives. So notice that in the first one we've got 1 and 0 for our partials, and that just gives us that. In the second, both partials are 1. And then in the third, the first one's 1 and the last one is negative 2. So notice that we've got negative 1 plus lambda 1 in all 3. And we're going to use that as our first step in eliminating our Lagrange multipliers. So the natural log of P sub g is the natural log of P sub r plus lambda 2. That comes from that negative 1 plus lambda 1 common to both. And similarly for the P sub b. So I've multiplied that top equation by 2 because that's going to allow us to cancel the lambda 2 terms. And using the properties of the logarithm, I can take the 2 as a power of P sub g, combine, and we're going to get this sum on the left is equal to 3 P sub r on the right. Using our properties of logarithms, we can take that as the log of a product equals the log of P sub r cubed. And therefore, we have to have p sub g squared p sub b is equal to p sub r cubed. And we're going to combine that with p sub g is equal to 2p sub b. This is one of our constraints. So that's going to mean we substitute, and we're going to get 4 p sub b cubed is equal to p sub r cubed. In solving, we get p sub r is 4 to the 1/3 power p sub b. The sum of the probabilities is 1, but again, p sub g is 2p sub b, so that's p sub r plus 3p sub b is equal to 1. And we solved for p sub r in terms of p sub b, and so we have p sub b is equal to 1 over 3 plus the cube root of 4. And that is our optimal value for p sub b, our argmax. So now we have the argmax for p sub b, and we can use our constraints to figure out what p sub g is and also what p sub r is. And that's about 0.346 as the probability of red, and about 0.43597 for the probability of green, and twice the p sub g star is twice the p sub b, which is 0.217988. So this is our maximum entropy model for this process. Now, we can also apply the maximum entropy principle to data, which gives us a maximum entropy model for data. So our third example is a process with 3 numerical outcomes, -1, 0, and 1. Here's our data, and we're told that the average is 3/7. That's not given by the data, but actually told to us from somebody who knows. It's a constraint. So that means our probability distribution looks like this and has to sum to 1, and the expected value has to be 3/7. In other words, these are our constraints. There's our Lagrangian, and we take the derivative with respect to p sub y, and there's our familiar friend, the negative natural log of p sub y minus 1 plus lambda 1 plus lambda 2y. The derivative is 0, and lambda p sub y is -1 plus lambda 1 plus lambda 2y. And therefore, p sub y is e to the -1 plus lambda 1 plus lambda 2y. And notice this is the probability function p of y as a positive number times an exponential. That's going to be important very soon. But for now, let's just use the constraints to eliminate our multipliers. So we had this relationship for y in general. Now for y equals -1, we get this because y is -1. And y is 0, we get just the natural log of p0 is -1 plus lambda 1. And there we have it for y equals 1. We can eliminate the lambda 1 by substitution. Now we have no lambda 1. We add these together, and we get the sum of the logarithms is twice the log of p0. Use our properties of logarithms, and we have this relationship. The sum of the probabilities is 1, and our average is 3/7, so that's this constraint. So we solve for P1 in that constraint and substitute that into our sum and simplify, and we have P0 is 4/7 minus 2P -1. And remember, we've got this P1 -1 P1 equals P naught squared. So we substitute that in. It's all in terms of P -1. Square it all out, and we end up with this. Now we can take this thing and multiply both sides by 49. Then we can factor and set each one of the factors equal to 0. And it's either P -1 star is either 1/7 or 16 over 21. Well, which one? Well, 3/7 plus P -1 has to be P1. But if I add 3/7 to 16 over 21, I get a number bigger than 1. So it can't be that one. So it has to be the 1/7, and therefore P naught star has to be 2/7 and P1 has to be 4/7. That satisfies our constraints. So if we've got a probability distribution on some y associated with some set of labels, then it's non-negative. But in reality, if we have a probability of 0, then that y is not going to contribute to our entropy. So we're only going to work with the strictly positive probabilities in working with entropy. So therefore, we're going to be looking at probability functions that are of the form c e to the f of y for some f of y on the set of labels in c greater than 0. So that means when we sum and get the p sub y is equals 1, then that's equivalent to saying p sub y is 1 over z e to the f of y, where z is the sum over the y's of e to the f of y. And this is what's known as the Gibbs form of a probability distribution. And z is called the partition function. Now, we also use Gibbs forms for probability density functions, and we'll do this later, but just to kind of mention, if we've got a continuous random variable x, then the cumulative distribution function is p of x, and its derivative, if it exists, is the probability density function, and it's non-negative, and we can therefore also assume it's in this sort of Gibbs form. Now, an expected value constraint or constrained expectation on a variable y is the expected value. We're given some kind of a function, and then the expected value of that function of the variable, capital Y, is the usual definition of expectation. And typically there are many of these, capital K of them. So let's look at an example. Suppose we have 5 classes or numerical labels or outcomes. And in this case, y is going to correspond to -2, -1, 0, 1, and 2. Here's our predicted labels. So we ran through our classifier and we got these predictions. And our data, therefore, is these predicted labels. And the average for the data, in this case, it turns out the average of these numbers is 0. And so our first constraint is that the expected value of capital Y is 0, which looks like this. The absolute value of the data is just where you take the absolute value of everything in the data set. And it turns out that the average for the data is 0.8, or for the absolute data, I'm sorry, is 0.8. And this is another constraint. Looks like this. So now we want to maximize entropy such that the sum of the probabilities is 1, the expected value is 0, and the expected absolute value is 0.8. Here's our Lagrangian. We take our derivative, get our familiar friend, this time with the lambda 3 times absolute y corresponding to our absolute constraint there. The derivative with respect to p0 is negative p0 minus 1 plus lambda 1. Boy, haven't we seen that many times. And therefore we get this, and the rest of them are of this form. And we can substitute the natural log of p0 for the negative 1 plus lambda 1. And then we can solve for p sub y. And notice p sub y is going to be p naught e to the lambda 2y plus lambda 3 absolute y. So now we can get for the other values of y. For y equals -2, y equals -1. And notice each one of these is p naught times an exponential. Now notice what we can do in p1 is we can add and subtract a lambda 2. And notice that means that the first part, e to the negative lambda 2 plus lambda 3, that's actually p negative 1. So we now know p1 is equal to p negative 1, e to the 2 lambda 2. And likewise, p2 is p to the negative 2, e to the 4 lambda, if you look at what we've done there. So notice now we use our first constraint, our expected value constraint, and we substitute, and we're going to just say C is e to the 2 lambda 2, some constant, and that's going to give me p negative 2, 1 minus c squared is equal to negative p negative 1, 1 minus c. And notice if c is less than 1, then c squared is less than 1. And if c is greater than 1, c squared is greater than 1. And therefore, this could only be possible if c is equal to 1. In other words, lambda 2 is equal to 0. That's the only solution, c equals 1, to this equation. So we now have, simplifying, there's no lambda 2 anymore. We've got our probabilities are p naughts times exponentials with lambda 3. So let's figure out what lambda 3 is. Well, notice that p negative 2 is equal to p2 and p negative 1 is equal to p1. So p1 squared is p naught squared e to the 2 lambda 3. But then if I divide by p2, that's the same as dividing by p naught e to the 2 lambda 3. And we get some cancellation. And we get a single p naught. So p1 squared is p naught times p2. Now we use our expected absolute constraint. And we replace and get 2p1 plus 4p2 is equal to 0.8. And then p1 is 0.4 minus 2p2. And now we've got two equations and the two unknowns. And we can then use our sum of the probabilities equals 1. And now we've got all we need to solve. And we get p naught is equal to 0.2 plus 2p2. And again, we're solving these equations. So this is all just mechanical. I don't want to put too much emphasis on the importance of this. This is all just basic algebra. But you do your basic algebra and you get some solutions. And it's either 0.8 or 0.1. But notice again, we can't use the 0.8 because that would make p naught bigger than 1. So we have p2 is 0.1, and that's the same as p negative 2, and p1 is 0.2, and that's the same as p negative 1, and p naught is 0.4. So these are straightforward calculations. And let's take all this that we've been doing and let's summarize it. So suppose we have our data as some kind of class labels, and we want to maximize entropy subject to expectation constraints of this form. So here k equals 1 corresponds to our sum of the probabilities equals 1. So that means our B1 is just 1. And this will be the constraints k equals 2 to capital K. Our Lagrangian looks like that. We take the C sub k's to be these expected values minus B sub k. And notice that the derivative with respect to P sub y is just F sub k of y. And there's our familiar friend. The derivative is 0 with respect to P sub y if the natural log of P sub y is negative 1 plus lambda 1, this linear combination. But we know what those are. Those are these function values. So I can exponentiate and get P sub y is either negative 1 plus this linear combination over the lambda sub k's. And that's going to give me some constant. And I'm going to write the constant as z inverse. Remember here, z is a constant. So I'm going to find 1 over z. And to do that, I notice that the sum of the P sub y's is going to be the sum of the z inverse, e to this linear combination. But that sum can be interchanged with the z inverse, and the sum of the probabilities is just 1. So that means my z is the sum y equals 1 to r e to the lambda 1 f1 of y up to lambda sub k f sub k of y. So in other words, we have a theorem. The maximum entropy distribution for y is P of y is 1 over z times the exponential of this linear combination of the functions that are applied to the labels, where z is the sum of the exponential of all those, is the partition function, and the lambda 1 to lambda k are constants that we've determined using the constraints. That was all that straightforward calculation we were doing to figure out how to what these lambdas were and what to actually put in there.